We're going to go and continue our adventure in evaluating improper integrals. In the last video, we looked at type 1 integrals. Now, in part 2, we're going to look at, well, what comes after 1? 2. So we're going to look at type 2 integrals. Instead of integrating out to, say, infinity or minus infinity, we're going to go ahead and evaluate integrals where we might have to go to or through a discontinuity. Oh, we probably haven't heard that word in a while before. Don't worry, I'll show you what it means. Let's just get right to it, huh? So we have an integral here, okay? The integral from 0 to 2 of 1 over x minus 2 cubed dx. We want to evaluate this or show that it diverges, okay? Now, remember, we say that the improper integral is divergent if, once we take the limit is infinity or minus infinity. Otherwise, we say it's convergent, and we assign it the value of the limit. So now the question is, well, how do we know this is type 2? Well, let's go ahead and draw a picture. So I'm going to go ahead and give a rough sketch of what this function looks like. It's not going to be the best sketch here. So this dotted line is going to represent x equals 2. And I'm going to go ahead and draw some approximation of this here. Okay, so we get this hyperbola looking thing. And the area that we're concerned about, what this thing represents, is this area which I'll shade in our usual color, magenta. Okay, the integral from 0 to 2, so we have this magenta area here. Okay, the question is that pink area finite or not? That's the question that we're trying to answer, if it's finite or not. Now, of course, you can look at this and see that it is a type 2 integral by graphing it, and we notice that at x equals 2, there's a problem. We have the asymptote. Okay, if I plug in x equals 2 to the function, I get a 0 in the denominator, and as we all know, if we try to divide by 0, the universe explodes. So the question is, how do we handle this? Well, we're going to have to recall something from Calculus 1 right at the beginning where we talked about limits, and we're going to have to actually do this as a one-sided limit, okay? Now, notice that in the picture here, I'm only coming at, let's do this different color. I'm only coming at the problem area, x equals 2, only from the left, okay? Notice that I'm only coming at this from the left, from below, so we're going to go ahead and phrase this as a one-sided limit. So let's go ahead and write our original integral. And we're going to go ahead and cast this integral as a limit here. It will be the limit as t approaches 2 from below, okay, 2 minus 2 from the left, okay? And it's going to be the integral from 0 to t of 1 over x minus 2 cubed dx. Now, remember, just like with any improper integral, we're just going to go ahead and evaluate the integral, and then we're going to go ahead and take a limit, okay? We're trying to look at a limit of some sort of function, this area function that's represented as the area under this curve, this pink area. Well, how do we integrate this thing? Now, of course, you can do a u substitution and shift some indices, whatever. But remember our base integral, right? Okay. Anytime I'm integrating, let's go ahead and write this down here somewhere just as a nice fact here. If I integrate 1 over x minus h to the p, okay, and I'll say this is for p different from 1, okay, this integral, okay, we have to think about this with the power rule, okay? So we rewrite this as x minus h to the minus p, okay? And now we add 1 to the exponents, not zoom out, okay? So we zoom back in. There we go. Everything's nice and fine. So we go ahead and add 1 to the exponent. So x minus h to the minus p plus 1 over minus p plus 1 plus a constant. Okay, so we have this base integral. That's exactly the result we're going to use here. So we have in black, okay, there we go. We have the limit as t approaches 2 minus of, well, we're going to go ahead and add 1 to the exponents, okay? So I'm going to kind of skirt some steps here, okay? So p here is equal to 3. I'll go ahead and write that here just for us. P is equal to 3. Okay, so we'll have, let's write it down, x minus 2 to the negative 3 plus 1 over negative 3 plus 1. And we're evaluating this between t and 0. Okay, and just to make our lives a little easier, I'm going to go ahead and write that in the usual way. So this is now just, well, the denominator, negative 3 plus 1 is negative 2, and the new exponent is negative 2. So 1 over, or rather, negative 1 over 2 times x minus 2 to the 2. Evaluate on the boundary. And now, the name of the game is just the same, right? We plug in top minus bottom, and we'll just have to take a limit at the end. So we have this limit here. Okay, I'll go ahead and write everything in. So we have negative 1 over 2 times t minus 2 squared, and then minus, let's just go ahead and write that in for completeness sake. Okay, minus minus, okay, 2 times 0 minus 2 square. Okay, we're trying to find the limit here as t approaches 2 minus. Now, when we clean this up a little, we'll get the limit as t approaches 2 minus, okay, of minus 1 over 2 times t minus 2 squared. Minus minus is a plus, okay. Negative 2 squared is a 4. Positive 4 times 2 is an 8. All right, so I have this nice looking thing. But now we need to figure out how to handle this limit here, okay? Well, think about, okay, the picture, the one-sided limit here. If I tried to plug in 2, okay, well, of course, I get a 0 on the bottom, but I have a 1 at the top. So don't think L'Hopital's rule here, okay? We're going to talk about that in a second, okay? Just because you get a 0 in the denominator doesn't mean you use L'Hopital's rule, okay? Please review that. So what happens here? Well, as t approaches 2 from the left, okay, the denominator gets closer to, say, a positive infinity, okay, because I'm going to square something that's a positive, okay? And, well, what happens here? And actually, I misspoke here. Let's go ahead and write things down so I don't mess this up here. So we need to look at that thing here. So if I think about the graph of that function, okay, we have something that probably looks like this. There's 2. Okay, if I look at the graph of that function, okay, I get something that looks like that, the volcano shape pointing down. Okay, it's going to minus infinity as a whole, okay? So this whole thing, okay, and watch the limits refresher video if you haven't, okay? That whole thing goes to minus infinity, while I have a constant and then minus infinity, all right? So what happens here? Well, this whole thing goes to minus infinity, okay? Because that first term, the term I have highlighted in yellow, will always be going towards minus infinity. It'll be large and negative. I can't control it, okay? So we say that the limit is minus infinity, and thus the integral diverges. So in a sense, the original pink area here has infinite area, okay? Now remember, we have to be very careful with these one-sided limits, and when we have a 0 in the denominator, okay, and especially in the case where we get something that looks like a 1 over 0 type limit, we have to think about these one-sided things, okay, are base things from calculus 1, okay? So think about that volcano shape here. All right, let's move on to another one here. Okay, so it doesn't look too bad. 0 to 2, integral of 0 to 2 of x log x dx. Well, why is this here? Well, remember, okay, that the log function is only defined in the real numbers, okay? It's only defined for positive real numbers, strictly positive real numbers. So can I take the log of 0? Well, no, you can't. Let's draw a picture of what this thing would look like. This is just a rough approximation, okay? An artist's rendering, if you will. And by artist rendering, I mean someone better than me, okay? I think, if I remember right, it should look something like this. Let's see, when x is equal to 1, we have 0, okay? Because log 1 is 0. Okay, and I think we should have something that looks like... you know what? Instead of boring you with the details of me trying to reconstruct this picture, I'm going to go ahead and take a peek at Desmos. I'll be right back. All right, I've spared you the gory details of me trying to wrap my brain around stuff, but if we draw the picture of the integrand, this is what it looks like. Okay, now, of course, we have an issue here, okay? We're going to make a note here, okay? That log of x goes to, well, it goes to minus infinity, as x approaches 0 from above, okay? That's something that we need to have, okay? As we take the limit, as I do something here real quick. There we go. As we take the limit of that thing here, okay, we're going to have a problem. So we're integrating to an asymptote, a discontinuity, so we have to go ahead and treat this as an improper integral. So we're going to go ahead and rewrite this. It's an integral from 0 to 2 of x log x dx. We're now going to take the limit here as t approaches 0 plus 0 from above, okay? We're only approaching 0 from the positive direction. Okay, now we're integrating from t to 2, x log x dx. And we've seen integrals of this type already in the integration by parts section. Please go ahead and watch that for how to handle integrals of the form x to the p log x. Okay, I'll go ahead and go through the steps one more time, okay, for how to do this. So we go ahead and use parts here. Okay, so we're going to go ahead and set, let's do this color here. We'll set u equal to log x, dv equal to x dx. Okay, du is equal to 1 over x dx, and v is equal to 1/2 x squared. Okay, and now as usual, we follow our path, okay, the integration by parts formula. All right, so we have now, let me go ahead and put this down here somewhere. Let's actually shuffle all this here. There we go. It looks a little better. I think I have enough room here. Okay, so now we have the limit as t approaches 0 of, okay, we're going to go ahead and apply the integration by parts formula, u times v, so 1/2 of x squared log x, minus the integral of v to u. Oops, and of course we have to evaluate on the boundary. Okay, and then it's going to be minus the integral of v to u. Now, v times du, we have a x squared times 1 over x there, which nets me an x here, okay? So we're going to have this integral here from t to 2 of 1/2 x dx. Okay, just take a note here, all right, that x squared times 1 over x is just x, okay? Now, that last integral we know how to do. It's pretty easy. Just use the power rule. Okay, an antiderivative is going to be 1/4 x squared. Okay, so we can turn this into one giant evaluation step here. The limit as t approaches 0 plus, okay, 1/2 x squared log x minus 1/4 x squared, evaluated on the boundary. Okay, now we just plug stuff in. Okay, and the good news here, okay, some stuff will look a little nice. Okay, so we have the limits. I'm dropping frames here. That's not good. Gotta wait for it to catch up. Oh boy. Sorry about that. T approaches 0 plus. Okay, if I plug in 2, okay, 2 squared is 4, divided by 2 is 2. Log 2. Minus 2 squared is 4, divided by 4 is 1, okay. Check that, please. And then minus, now this is where the fun part happens here, okay. Minus 1/2 t squared log t minus 1/4 t squared. Now, this highlight bit here, okay, that part in the light blue, we have to figure out the limits, okay? Now, we can see, right, 1/4 t squared, that's going to go to 0 as t goes to 0, so we don't really need to worry about that. In fact, let's just go ahead and make a note there. Not with that thing, okay? This thing goes to 0 in limits, okay? But now how do we handle t squared log t, okay? Well, we plugged in 0. Well, we get 0 times log 0, which is minus infinity, and I'm using bunny quotes for that. Oh dear, 0 times infinity. We have to use L'Hopital's rule. Okay, so we're going to go ahead and do a side calculation here, okay? Here's our side calculation. We need to compute the limit as t approaches 0 plus of t squared log t, okay? Now, the 1/2 is going to come for the ride. We just, remember your constant multiple rules for limits. You can just shove them outside and save them for later. Okay, so how do we handle this? Well, we're going to manipulate this into a form that seems familiar. If you remember your L'Hopital's rule, right? You can use L'Hopital's rule if you have a limit of the form infinity over infinity or 0 over 0. But Sean, this is 0 times infinity. I know, but we're going to bend the rules a little. What's going to happen is I'm going to write this as a fraction now, okay? Because I want that infinity over infinity or 0 over 0. I'm still going to have log t. But on the bottom, the t squared, I'm going to make that a 1 over t squared. Why? Because look what happens. Okay, this here gives me a infinity, well, really a minus infinity over infinity type thing, which is still infinity over infinity in a sense. So L'Hopital rule. So we use L'Hopital. Okay, and if you remember from the limit refresher video, okay, L'Hopital's rule, if we have an infinity over infinity or a 0 over 0 case, when we take a limit, what we're going to do, we take derivatives of top and bottom separately, okay? So we're going to go ahead and use L'Hopital's rule here. Let's go ahead and give me some space above my head here. So we're going to do the limit as t approaches 0 plus of the derivative of log t is 1 over t, and the derivative of 1 over t squared is minus 2 over t cubed, okay? Remember, power rule just for that, right? Net minus 2 times t to the minus 3. Okay, and how do we divide fractions? We'll keep, change, flip, right? Keep the top, change to multiplication, and then flip the second fraction. And now take a look, right? I have a t cubed over t, which is a t square. All right, of course, I still have the minus 1/2 there. Minus 1/2 t squared, and this is 0. So the limit there is 0. So check it out here. This whole thing goes to 0. And so in limits, okay, we just have all this left over, right? All we have now is 2 log 2 minus 1, and we're done, okay? This one was a little hairy to work with, okay? Because we had to do that side calculation here, okay, with L'Hopital's rule. Okay, we had to turn this t squared log t into a clever fraction that gives us an infinity over infinity, okay? And in the end, we got that this is 0. Now, you can show this again by other methods. You'll probably learn some power series methods if you're clever for that. But the traditional way is to just use L'Hopital's rule, okay? So, see if you can find the pattern when it's not just t squared, but any power of t, okay? Something like, say, t to the p log t. What happens there? You'll probably find the pattern. All right, let's go on to our last one here. I have this integral, all right? Minus 1 to 2 of 3 over x squared. Just for kicks, let's draw the picture. I know I have an even exponent here, so I'm going to get the volcano shape. The asymptote at 0. Okay. So I have my volcano shape. All right, but now let's take a look here. We have minus 1. We have 2. Okay. And the area that I want is here. Now, the question is, does this area make sense? But notice that I'm integrating not just to with this continuity, I'm integrating through the discontinuity, okay? I'm integrating through the asymptote. So this is still a type 2 integral, okay? It's still a type 2 integral. But what do I do here? Well, remember that I'm allowed to chop up integrals into multiple pieces, okay? So what I'm going to do is I'm going to make a cut here. I'm going to cut my interval, okay, at 0, and now I have 2 separate pieces, okay? Let's see if I can convince you of that, okay? So I'm going to just draw a rough picture here. So this kind of shape here, this area is going to be equal to the sum of 2 parts here. It's going to be the sum of this part. Okay, that's on the left. And on the right here, which I've messed up, so oops. Isn't this fun? So on the right here, okay, we have this piece, okay? So we're going to chop this into two pieces. Okay, that's what we're going to do. We have this area plus this area. Okay, and those two should glue together to give me the whole volcano shape here. But the question is, does that area make sense? So we're going to go ahead and cut this into two integrals here, okay? So this integral from -1 to 2, going to express this as the integral from -1 to 0, because that's our problem point, okay? 3 over x squared. And then we're going to continue integrating from 0 to 2, okay? Now, this actually is two type 2 integrals that we're going to glue together. And the result says, okay, that in order for an improper integral to converge, if I have to break it up into finitely many pieces, the sum of those has to converge. What that means is all of those integrals must exist. If one of those integrals fails to exist, we have a problem, and we say that the integral is divergent. So I'm going to go ahead and break this into two parts. I'll call this, say, I minus and I plus, okay? So I'm just doing this two integrals here. So I minus is the left piece here on the negative part. Now you kind of see why I called it I minus. And then likewise for I plus, okay? If I can show that one of these integrals fails to exist, then you can probably guess why I'm doing that, because spoiler alert. Aw, man, don't click off already. Come back. Okay. If I can show that one of these integrals fails to exist, I'm done. So we're going to go ahead and do that. So consider I minus, okay? Let's consider the integral I minus here, okay? So we're going to go ahead and look at the integral from -1 to 0, okay, 3 over x squared dx. Again, we have a problem point here, and for I minus, okay, if you look at the picture, I'm approaching the problem from the left, okay? So we're going to go ahead and take the limit here as t approaches 0 minus here, okay, -1 to t, 3 over x squared dx. It's just our power rule again, right? So we have a limit here. Find the antiderivative. So that's going to be -3 over x. Okay. Use your power rule. Do the evaluate step. Okay, we can kind of move on to this side. Okay. So we have -3 over t, and then minus is a plus. Okay. Let's just write that down to be safe here. -3 over -1. Oops, and I forgot an important thing here. Folks, remember whenever you're working with limit calculations, make sure that you carry the limit operator through, okay, until you're done. 0 minus, okay? And this is where we have to also be careful with the signs, right? Because we have minus over minus is plus, but then I'm subtracting a plus, so that's a minus. So we get the limits as t approaches 0 minus of -3 over t plus 3. Well, what happens here, okay? Well, we had a limit just like this, okay? If I approach 0 from the left, okay, I'm basically getting 3 over very, very, very small negative number, which is a very, very, very big positive number. Well, we have a minus sign there. It doesn't really matter. The point is, okay, if I put in a very, very, very tiny number, 3 divided by a very, very, very tiny number is a very, very, very big number. So the limit here is infinity. Okay. The limit there is infinity. So as a whole, this limit is infinity. Okay. But do we have to do the work for the other integral? No. See, if I know that one of these integrals does not converge, meaning if one of these gets much, much larger without bound, then I obviously can't control the entire thing. Okay, if I have one issue, that's it. Okay, and we're going to come back to that when we talk about sequences in the series. Okay, the point is here, okay, because, and that's a terrible looking B. So because I minus is divergent, the total integral is divergent. Okay. So the whole integral diverges. Okay. So let's write that explicitly. That is, okay, this integral that we wanted to find here, what was it, to 2? Yeah. Okay, this integral is divergent. Okay? Because one of them failed, the entire thing fails, okay? It's, think about it like something in series, okay? If one component fails, then all the other components will fail. That's the idea. Okay, you can also show this with the integral I plus, okay? And I encourage you to do that, okay? Show this for the integral I plus. Okay, same results, but it's enough to show that one of the integrals fails to converge. Okay, so as we've seen here, improper integrals are very, very, very delicate. Okay, if we're integrating to infinity, sometimes they might be well behaved. If we're integrating through or to with this continuity, we got to be extra careful. And this is where we have to think about our one-sided limits. This is where we have to really think about some of our basic limits, okay? And this is where drawing the pictures can really help, okay? So that's type 1 and type 2 integrals, okay? But maybe there are some integrals that we can't evaluate, but we just want to see, well, are they nice? I'll see you in part 3, and I'll see you in the next one.